Good morning, everybody. I'm really happy to be here talking about what I do for a living, which is looking at awesome type 1 diabetes research and trying to make progress on that front as much as possible. So um, the title of the talk that I originally had was the pretty bland JDRF research update, but then I thought maybe that's being a little disingenuous, because really what it is a very, very exciting JDRF research update. So I hope you'll agree with me at the end of the talk. Just a little bit about me. I am a biomedical engineer by training. I grew up in Denver, Colorado. I did my undergrad in chemical engineering at University of Colorado. And then I went on to specialize in specifically artificial pancreas algorithm technology in grad school at the beautiful University of California, Santa Barbara. So I have been in type 1 diabetes research now for I think about 12 or 13 years, and really I've been laser focused on, like I said, different ways that we can control blood glucose through the automation in an artificial pancreas application. And that's what I do at JDRF. I'm kind of new to JDRF. I've been there for approximately 6 months now, having come from industry. I worked at the unfortunately now defunct Animas division of Johnson & Johnson for many years as its algorithm scientist, and we were really close to coming up with our own artificial pancreas device. Unfortunately, it's a very difficult business model, and we just didn't innovate fast enough, quite frankly. So there was an unfortunate ending to that story, but then I was really lucky to have landed at JDRF last fall. So my role is director of research. We have a handful of different directors that specialize in different program areas, and I'll talk about some of those program areas today. I specialize in artificial pancreas and also metabolic control, which is closely related. Both program areas treat the symptoms of type 1 diabetes as effectively as possible. It's just that the artificial pancreas program area does it through really a device-based approach, and then the metabolic control area does it through mostly different kinds of really creative drug approaches, as Adam was mentioning earlier. So a couple of pictures here. There's two goofy guys that I live with in the upper right-hand corner, and then the one that's not so furry is my son, who's about 4 months old. And then this is majestic Colorado, and then this is just beautiful Santa Barbara, and now I'm back to this stuff in Philadelphia. So, but it's okay because I like the snow. So, point of this slide is that we've come a very long way in not so much time. Not so long ago, we have this guy on the left here wearing the world's first artificial pancreas. It's a monstrosity. It also needed direct access to the veins, so it was obviously not a sustainable thing. Now, as many of you know, the insulin pumps and artificial pancreas devices that we have are more like the size of cell phones. We have a couple of goofy things here like urine testing, which really isn't that effective, and so we've come a long way with that. A couple of other archaic developments, which are part of the process of research and development. You got to try to just take the first step and then expand from there. So we've come a long way, but we certainly aren't there yet. We realize that we have a lot of work to do at the JDRF and other research agencies. So just a couple of figures for you. On the left is the percentage of people that are not meeting their target A1C levels, and this is to the tune of 70 to upwards of 90%, depending on age brackets. So there's a lot of work to be done there. On the right, there's the two really nasty things about type 1, which is severe hypoglycemia and DKA. Again, sort of as a function of age, the percentages are, and this is percentage of people reporting at least one of these events in the last 3 months, so pretty recently, and they're pretty high. So we realize that there's a lot of work to be done on that front as well. So our plan and impact, as was kind of touched on earlier. So we have a vision, which is a world without type 1 diabetes, and we have a mission, which is to accelerate life-changing breakthroughs to cure, prevent, and treat type 1 diabetes and its complications. So then if we kind of break it down into the three high-level work streams that we think about at JDRF, it's to cure, which is clearly a high priority for us, and we are very, very committed to finding a cure. And that's by restoring normal glucose control and certainly preventing those long-term complications. But in the meantime, we're exploring things like prevention, which is to prevent this not well understood autoimmune attack of the pancreatic beta cells in the first place. And then also, if we could preserve beta cell function and prevent dependence on exogenous insulin, that would also be great. And then my focus really is on the treat category, which is to improve glucose control. We're always interested in simplifying management. So, improving outcomes is admittedly probably our top priority, but making the experience and the quality of life as good as possible is certainly another area that we focus on very much. And that kind of has to do a little bit with the daily burden of type 1 diabetes as well. And then again, we're looking to prevent long-term complications by effective treatment of type 1. So a word about our research programs, which was shown just a few minutes ago here. And I'll touch on each one of these, but I will be focusing on the artificial pancreas developments recently and focuses going forward. So we have artificial pancreas and metabolic control. We have complications, beta cell replacement, and then sort of in one bucket, we have regeneration and immunotherapies, and then certainly prevention is up there too. So this is a good graph, I think, that shows the progression of type 1 diabetes from just being at risk and having 100% of your beta cell mass still, all the way down to established diabetes where you have very little of your original beta cell mass still left. Almost all of your beta cells are gone. So diagnosis sometimes happens around here, which is when there's been a pretty good amount of destruction of the beta cells already. So the program areas as related to this timeline of how your beta cell mass decreases are sort of as follows. So in the prevention category, we're looking at this sort of stage in the journey of a person with type 1 diabetes, basically up until diagnosis. So that's where that program strategy comes in. It doesn't really make a lot of sense afterwards, but there's other program strategies that make sense after that. So that's prevention. In regeneration and immune therapies, it runs almost the gamut of this journey. So there's a lot of research that's looking at people in pre-diabetes phase all the way through established diabetes. And beta cell replacement, sort of by definition, if you've lost a lot of beta cells, then the replacement program comes in to try to get those beta cells back, and there's a couple different ways that we're looking at to do that. Metabolic control and artificial pancreas, like I sort of mentioned earlier, are both really when you looking at established diabetes, and it's a way to treat the symptoms very, very effectively as possible, just through different approaches, kind of fundamentally different approaches. So in the prevention category, our goal here is to prevent or delay dependence of insulin on dependence of exogenous insulin. We want the body to still be able to be insulin independent and make as much insulin as is needed for metabolism. So there are multiple potential prevention strategies that are in clinical testing. Some of these include the use of oral insulin to delay the onset of type 1 diabetes. So that's delaying the onset, which is good, but it's just part of the problem here. And that would be in people that are at high risk, that have first generation family members that have type 1 diabetes, and then various others are at earlier stages of development. So for those folks out there that might be at high risk, or children of people that might have type 1 diabetes, we highly encourage the use of these screenings, and there's some organizations here that can do these screenings. Basically what happens a lot of times, or at least historically, is what happens is you have maybe no idea that you're going to develop type 1 diabetes until you end up in the emergency room with DKA. And then you not only are in the emergency room dealing with your DKA, but you also get a diagnosis of type 1 diabetes. So effective screening can greatly reduce the incidence of DKA, and that's really, really important because DKA is very, very bad. So I would encourage you to, if you haven't done so already, to check out some of these organizations. So restoration through regeneration. So this is when we want to promote the survival and or regrowth of the body's beta cells. So in this one, we have JDRF funded studies making good progress toward developing novel drugs and even identifying existing drugs, repurposing them, that may be effective in enhancing beta cell survival and regeneration. We got technical difficulties here. Can you advance by one? So another kind of way to think about restoration is through immune therapies. And here, what the JDRF focuses on is preventing or stopping the immune system attack on insulin-producing beta cells. I know very little about this. This is a really, really interesting category of ways to look at preventing type 1 diabetes. The immune system is a really interesting system, and unfortunately in type 1 diabetes, it is out of balance. So for some reason, the aggressive cells in the immune system start killing off the beta cells, and the peacekeepers in the immune system just aren't there to restore the balance. And so you just have this bad feedback cycle where more and more beta cells are killed off. And so what we're trying to do here is understand the mechanism better. By understanding the mechanism better, we can hope to try to figure out what can stop that or slow that mechanism. So for this one, we're looking at clinical testing also, and we're supporting earlier stage development of promising new and next generation approaches. These are, like is indicated here, pretty early stage, but we have very smart scientists that are looking at all kinds of different immunotherapies. So this is another really interesting way to approach, treating type 1 diabetes. If your body kills a bunch of your beta cells and you're left with very few beta cells, let's put beta cells back. So that's basically what the beta cell replacement program is. And even though it sounds simple or like a brute force approach, obviously the solutions have to be much, much more elegant than that. So in this program, we have demonstrated that the transplantation of donor islets could temporarily reverse the disease in people in type 1 diabetes. It's a very exciting result. And the procedure, moreover, is approved and reimbursed for people outside the US who have serious hypoglycemia unawareness. The problem is it's not for everybody, and it's not even currently available to everybody. The couple of graphs I have here are just, I think, totally just really impressive with what the possibilities are. So before the islet transplantation, we have what looks, unfortunately like the norm for a lot of people with type 1 diabetes, which is blood sugars all over the place. And this is shown maybe a week or so of data. On the right, after the islet transplantation, you pretty much get rid of the symptoms. So it's exciting, but the limitations are that you are going to have to rely on donor islets, which are always going to be scarce, and you still have this autoimmune thing going on in your body, so you're still going to have to figure out how to suppress those autoimmune effects. And so some of our strategies to overcome these limitations are to figure out a way to actually produce sort of sustainably insulin-producing beta cells. And there's a couple of different techniques that are being looked at in terms of how to produce beta cells. And then delivery systems that would keep cell alive and functional without that broad immune suppression. So I think this is a really, really interesting category, and there's good progress being made on it. So in the complications area, we're focusing mainly on kidney and eye disease. We're looking to preserve kidney function and eyesight. The key here is through early intervention. Oftentimes, some of these bad complications are not kind of like this. It's the same way with type 1 diabetes. The complications themselves aren't diagnosed until it's a little bit too late, and the mechanisms have already gone through. So scientists can't really understand what caused these complications in the first place. So that's the key: is to understand early how these mechanisms happen, so that we can develop therapies or treatments for them. So to that end, we're trying to have a big effort to identify biomarkers, which are basically measurable signs of biological processes early on in these complication development stages that would enable a couple of things. It would enable us to understand what's going on, and then that way we could develop better therapies. And what we could also do is have better designed clinical trials. If you do a clinical trial with the wrong population, then you're not really getting to the crux of the issue. So if we do a clinical study with the right population, then we could possibly make a lot of progress there in preventing these complications. In metabolic control, so I'll get into this one just a little bit. We want to improve glycemic control and restore the body's overall biochemical balance without increasing the burden. So this would be a drug-based approach. You would be free of devices, or at least attached devices, insulin pumps. You take medication yeah, so that's the drug-based approach. I think next slide. So smart insulins are a really interesting and exciting kind of early technology that Adam was mentioning earlier. So there's a couple kinds of smart insulins. I'll just describe two of them. So this one is called a glucose-responsive insulin, and basically what happens is there's a couple different very creative ways that these things are being engineered. One of which is you take an insulin molecule and you can attach another molecule to it, which would render the insulin ineffective. And that happens when the glucose concentrations in the body are low. Now, when the glucose concentrations rise, this other thing that's attached to the insulin actually breaks off of the insulin and gets attracted to the glucose, basically, rendering the insulin molecule active. And then the insulin molecule then can help in reducing blood glucose. So it's this really cool negative feedback mechanism that's totally based on chemistry. So there are a couple of studies that we have. There's actually a big initiative. We are sort of casting a wide net. We have a number of studies that are looking at early, benchtop type testing for glucose responsive insulins, and some of them are looking pretty good right now. And then the other kind of smart insulin that I just wanted to mention is another really cool insulin. So insulin is supposed to be delivered from the pancreas pretty much right to the liver. So there's this other category of insulins, smart insulins, called liver-targeted insulin, which is basically, again, you take an insulin molecule and you attach something to it, and what you're attaching to it provides basically a GPS that sends it straight to the liver. It's very cool. So then the body can understand what to do better with that insulin. It's kind of the natural process for insulin secretion and distribution. So, and then I'll get into a little bit more detail on the artificial pancreas, some of our recent achievements, some of our recent research priorities for now and also for the immediate future. And this is sort of the nearest and dearest to my heart because I've been working on it for a while, and I think there's some really cool things that are going on in this world. So this was a very, very high level roadmap of the development of an artificial pancreas device. In the first one, we just had a very simple device, which Medtronic did make, called a low glucose suspend. So with the use of a continuous glucose monitor, which is the key part of an artificial pancreas device, an insulin pump and an algorithm that's in the insulin pump could basically just suspend insulin delivery when glucose concentrations got to be too low. So you can define what you mean by too low. Basically, the outcomes are that you have less hypoglycemia. So this was a great first step, a very simple first step, but a good first step nonetheless. And I'm sure that even just with this, it allowed a lot of parents to sleep better at night. So then moving on, we have the predictive suspend, which is a pretty simple augmentation of a low glucose suspend, which is just instead of suspending insulin when you hit this low glucose threshold, you can just make a simple prediction into the future that you have a high probability of hitting that low threshold sometime, let's say a half hour or an hour into the future. So let's proactively suspend insulin delivery and possibly, make it so that you never get to that low threshold in the first place. So now those are kind of yesterday's news a little bit, I'm happy to say, because now we have the ability to get much more sophisticated in terms of the control and the algorithms that go into artificial pancreas devices. So the 3A and 3B are very exciting. 3A is a hybrid closed loop. The hybrid part means that although you do have this device that's making autonomous insulin delivery decisions to keep you safe and to keep your glucose in a healthy zone without your permission, you also have to intervene yourself when it comes to mealtime insulin. So that's what the hybrid means. It means that you have this controller that's doing some of the work, but also you have to do some of the work still. So in a hybrid system, basically, you're still going to be bolusing yourself insulin at meal times, counting carbs as accurately as possible, all those annoyances. But in the background, the controller is going to be doing as much as it can autonomously, automatically to enhance that control. Moving on, and I do believe it's on the horizon, a fully automated artificial pancreas device would get rid of that last little bit of responsibility by the patient in terms of dosing for mealtime insulin and take over and do a good job at it and really remove the patient from that closed loop. So in that, we're talking about full automation. So there's many reasons to celebrate. This is our own Katie Helm, who was a trial participant. She says that it's really changed her life and for the better. So the first hybrid system is approved, and I actually have a slide on that next. More systems are coming. I also have a slide on that just to give you guys an update. It's been shown in many, many, many clinical studies and research articles that these systems do improve A1C, they improve time spent in hypoglycemia, they improve time spent in range, which we usually think of as 70 to 180 milligrams per deciliter. That's an outcome that we really like at JDRF. And moreover, quality of life. There's also a couple of surveys, basically quality of life surveys that are validated, that are kind of accepted by the community, that look at your quality of life before you tried this system and your quality of life after you tried this system, and there's big improvements. We're looking at expanded use of technology in, quote, special populations. Basically, when you try to get a product approved, you typically look at sort of the bulk of the population, let's say adults with established type 1 diabetes, but there are certainly other populations that we want to expand labeling into, and so that's a priority for us as well. We're always looking, we have a team that is always looking at how to make coverage better for devices and therapies for type 1. And yeah, next slide. So 3 priority areas for us for the artificial pancreas program area are to enhance glucose control. I think you can go to the next slide. So to enhance glucose control, there's a couple of interesting ways we're looking at enhancing glucose control. I'll get into some of these in just a little bit. The use of additional inputs, kind of a more engineering way to approach things, but it's really exciting in this day and age of everything's connected. You have the Internet of Things, you have data freely flowing everywhere, so we're trying to take advantage of that and use it to enhance glucose control. We're looking at faster insulins and also other adjunct drugs. We'll always need insulin, some kind of insulin, but we're also looking at different drugs that we might augment an artificial pancreas system with. And in general, advanced algorithms. So again, we're kind of in this information age, and there's a lot we can do maybe with big data, artificial intelligence, that kind of thing. So we're looking at all of these things. Next slide. And then by reducing burden, I touched on this a little bit earlier, we're talking about, let's say, glucose outcomes aside, we're certainly very, very concerned with glucose outcomes, but let's also focus on ways that we can reduce the burden. I think when we reduce the burden, we might be able to see a big uptick in adoption. Maybe people that didn't want to wear a device because they didn't want to be tethered to something, and they didn't, that there were a couple of unpleasantries about wearing an insulin pump. Well, maybe let's look at that. Maybe miniaturization will help if we can get a really, really small patch pump out on the market. Increased automation, so that has more to do with sort of the mental or psychological burden. The more we can automate things, the less the patient has to think about it, the better the more reduced the burden is. And then, it's a pain, but you got to replace your infusion set every 3 days. You got to refill your insulin every few days. So we're certainly looking at, and then the CGM sensor as well. So we're certainly looking at ways that we can extend the wear so that you don't have to think about it as much, maybe half as much, or even a third as much. And then finally, expanding access and adoption. I kind of mentioned targeted subpopulations, barriers to adoption, and then a really novel effort by the JDRF compared to what we've done before is looking at open protocol artificial pancreas systems. And some of you might have seen this in some of the technology news. I'll get into all of these issues briefly here over the next few minutes. So, as was mentioned, we have the first hybrid artificial pancreas device in the market. This is the Medtronic 670G. Right now it's indicated for 14 plus years old, but there is another pivotal study that they're running which would expand the label down to, I believe, 7. And they would, they will certainly be looking to expand the label even more as they go forward. So this is that hybrid system I was talking about where you still need to bolus for meals. There's a couple of specs about the algorithm here where you can set your glucose target at either 120 or 150 depending on either your activity level or your level of comfort. And so it's out there, and it's a good device. I have a data slide on the next slide. So this is data from their pivotal study. The pivotal study is that study you need to do right before you get FDA approval to market and sell your device. So they looked at a lot of patients, 124. We're looking at, so the gray sort of envelope there is a measure of the spread of glucose concentrations over the course of a day in open loop, meaning not using this closed loop artificial pancreas device. And it's kind of all over the place. When you use the closed loop, you get this pink spread here, which is much, much tighter. Especially, I highlight those first 8 hours of the day or so, from midnight to 8 a.m., where you have this really nice tight control using the closed loop device. You come in for a nice soft landing right before you get up for the morning, basically, and so you, in theory, have fewer surprises in the morning. You wake up feeling better. You don't have to worry so much at night. So there's a lot of benefits here, and this is a really nice way, I think, to show those benefits of using a closed loop system. In addition, what you can't really see from this slide, but they've tallied the numbers, is you also get a decent reduction in A1C. In this case, it was a 0.5% just by using this system. So we're making progress. And then an update on the other. So right now, that's pretty much the only artificial pancreas device in the market, for better or for worse. It's good that there's one, but we love competition. We love choice. That drives prices down. That increases innovation. All that good stuff. So there are some other companies that are very, very serious that are either in the process of doing a pivotal study, as is the case with Tandem, who makes a touchscreen insulin pump. Insulet, who is famous for making their Omnipod, which is the patch pump that a lot of people like. Bigfoot is sort of this newer company led by a couple of very interesting individuals, one of whom used to run the JDRF, Jeffrey Brewer, and Beta Bionics, which is sort of a smaller outfit that ultimately is going to look at a dual hormone insulin pump, which would include not only insulin but glucagon. For now, they're actually just looking at the insulin-only artificial pancreas device. So if things stay on track, and we like to make sure that they do as much as we can, then there should be, you know, by the end of 2019, there should be kind of a selection of devices, and then it'll be kind of fun to see. You know, studies will be done to show what the pros and cons of each device are, and then patients can get informed a little bit and then make a choice as to which system might be best for them. And then so some of the current and near future priorities that are in the artificial pancreas program area that are very much on our radar are the development of user-centric innovations. So that has to do more with the user experience, quality of life, that kind of thing. Additional signals, I'll talk about that in a second. The next one is, you know, we're basically using one thing to control glucose right now, which is subcutaneously infused rapid-acting insulin. And we can do pretty good with that, but we're also looking at, let's take the next step. How are we going to get to that full automation that I talked about earlier? And there's a couple of approaches that we're looking at. One is to look at new insulins that are even faster than what's out there, looking at adjunct drugs, and then also maybe a little bit more creatively is looking at different delivery routes. So instead of delivering insulin subcutaneously, maybe if there's a really good solution that might not work for everybody, but it works really, really well for some people, by delivering insulin to a different area in the body, then maybe that's the route for some folks. And then the open protocol systems. So for the user-centric, these are just photos of 3 projects that we recently launched. These are not so much research projects, but they're what we call the industry discovery and development partnerships at JDRF. So these are agreements that we make with companies to, like I said, not so much research something, but actually develop a product. So we're very involved in that development process. We keep track of milestones. We make sure that they're on track. If a obstacle comes up, we do anything that we can to try to figure out how to fix it. So these are 3 young companies that are looking at novel insulin pumps, sometimes using different pumping technology than has been used before. They can get very, very accurate with these new technologies. They're all going to be very small. That was one of the main purposes of this effort. And then the one on the right, in particular, I wanted to highlight, very creative. It's a bandage-like pump. You can see it curves there. It can adapt to the curvature of your skin. And so they have this really cool idea, and we're going to do everything in our power to try to make that work. So there's a lot of interest in still developing good technologies for insulin pumping and for artificial pancreas. So there's no dearth of ideas out there, so that's a good thing. The next one here is additional signals. I mentioned we're in this Internet of Things age. Right now, as far as the input to the algorithm, we're pretty much just relying on the glucose signal that comes from the continuous glucose monitor. Well, this initiative, and we have about 5 or 6 interesting projects that, again, have been recently launched, so there's no data yet from them, but we hope that we'll make some progress on that soon. We're going to be looking at other things that can better inform the controller, not just glucose. We'll need glucose, but also exercise and things related to exercise like lactate levels in the body. We're going to look at how physiological stress can affect things and how we can maybe treat in response to signals that measure physiological stress. Possibly environmental conditions, the use of geolocation has been discussed. Those are sort of just ideas right now. And the other thing about this is we would also try to effect more user-friendly interactions. So instead of using an insulin pump, which is a medical device, maybe we transfer the interactions to the cell phone or some other thing that's a little bit more user-friendly. So and then this is this category of beyond rapid-acting subcutaneously infused insulin. This is an effort that we're going to look into, which is to infuse two drugs together, insulin plus pramlintide. What pramlintide does is it slows gastric emptying. So after you have a meal, it'll slow that emptying of food, convert it into glucose, so that the insulin that we infuse has a better chance of regulating some of those highs after meals, which is a big problem still. So this could be a really good thing, because this we could almost use basically the algorithms that we have now and the insulin pumps that we have now. We're just going to give ourselves a better chance to automate and control glucose by using this other drug here. And then I mentioned intraperitoneal delivery, so that there's pros and cons to this one. Nobody would argue that delivering insulin instead of to the subcutaneous tissue, but rather to this area in your body that's right next to your liver, nobody would argue that it results in better PK/PD, or insulin characteristics, that are more conducive to sort of what the body does naturally, so we can get better control, essentially. The problem is that how do you get the insulin into the IP space in the first place? Well, you have to have a catheter that goes there, basically, so you have to have an implant. It's probably going to be a pretty minor procedure, but a procedure nonetheless. You're going to have to probably go in for maintenance checks over the course of the year, but it could be, when it's all said and done, a lot fewer diabetes tasks than the current state of care. So there's pros and cons, and we're trying to figure out if that's the right move for us, if we should be making a push into that space. So it's kind of a hot topic right now. And then so finally, the Open Protocol Systems is this initiative that's really close to the hearts of our Chief Mission Officer, whose name is Aaron Kowalski, and also a trustee from the Helmsley Charitable Trust, who's also involved in funding type 1 diabetes research. Basically, what has happened is that the traditional development of artificial pancreas systems is slow. I'm kind of a living example of that. The chart I showed you earlier, things take time. And that's part of the process. The FDA is involved in regulating things, making sure the public stays safe. In the meantime, there's this whole community of do-it-yourselfers. They even have a hashtag. The hashtag is We Are Not Waiting, who have developed their own artificial pancreas algorithms. They've hacked into old insulin pumps. They've leveraged signals from CGM in order to create their own do-it-yourself artificial pancreas system. So there's this sort of convoluted system that they have because they've had to do this hacking. But the outcomes are anecdotally very, very good. So this initiative wants to kind of take a step back, understand what the outcomes are scientifically in a more fundamental clinical study sort of way. If there are problems, we need to know about them. If the outcomes are fantastic, then we want to make it so that more people can use systems like these. But we want to do it the right way. We want to incorporate all the key stakeholders, like the FDA is very important to this mission. All of the device manufacturers are certainly very important to this effort, and some other key opinion leaders. But essentially, we're working towards understanding if there's a possibility that we can have this more open or plug-and-play ecosystem, which would be probably tied to a cell phone. And then on the next slide, it's a broad initiative. It's going to really involve the whole community. So there's a couple aspects. There's the technical aspect, which is, just sort of technically, how do we develop devices that can talk to each other? That's pretty well understood. I would even say pretty easy to do. So that's not the problem. That needs to be done eventually, but that's not the problem. The problem are these other two issues, which are much more, they are just bigger things. They're going to involve, like I said, the community rallying behind an initiative like this, and the FDA blessing it and giving guidance to us and to the device makers. So that's the regulatory pathway. And then also It's how the world works. The companies are sometimes very hesitant because of liability issues. If something goes wrong, who's going to be blamed, who's going to be sued. So we want to understand, again, what the right way is to do this, what liability framework we can get so that the device makers will actually come to the table and want to produce things like this. So we have a workshop with the FDA set up in a couple months, which we've been planning for the last half year, basically. So it's going to take longer than that to understand where we're going to go, but the wheels are in motion, and we're going to do everything we can to see if there's a possibility for these kind of systems to be used. This was in the news a few times. I know Adam Brown from Close Concerns, I think, is talking later today. Close Concerns did a really, really good job of covering this story, and so did a couple of other news outlets. So there's a lot of excitement. We need to, maybe just take a step back, like I said, and just understand things. We want to do it the right way, and we're going to intend to do that. Just wanted to kind of show our spirit of collaboration at JDRF. Obviously, we don't do the research ourselves. We direct the research to a certain degree. We understand what our priorities are strategically. We listen to people like you guys. We stay up on research, but ultimately we don't actually do the research. We fund the research. So we need to partner with some of the absolute best academic minds and industrial outfits throughout the whole world. So we're really proud of all of our collaborations. And then just my last two slides. So there's a couple different ways. There's more than a couple different ways you can get involved, but I'll just highlight two from maybe more of a scientific perspective. So if you'd like to participate in a clinical trial where we look at exciting new therapies, then there's a way to do that systematically. You can go to our website here and see if there's anything that interests you and anything that's in your area. And we're always looking for subjects. Usually subject recruitment is difficult, although I've got to say, with a very engaged type 1 diabetes field, it actually seems to be easier than some other industries, so we're happy about that. We always need subjects. And then you can also, there's a network for pancreatic organ donors with diabetes, NPOD. You can go to the website and read about how you can do that, but that certainly will help people tremendously. So I'd encourage you to just learn more about it. And with that, I just want to say thank you so much, and it was a pleasure to tell you about the research that we're doing.